Today we are going to prove that this series converges based on the comparison test discussed in class. The first thing we are going to do is rewrite this series so that it can be easier for us to understand, as the sum from k equals 3 to infinity of 2 cubed to the k minus 1 over 9 to the k times 9. Here we just use basic properties of exponents, that 9 to the k plus 1 is equal to the 9 to the k times 9, and that 2 to the 3k is equal to 2 cubed to the k power. So now we can further rewrite this, and since there is a constant here, we can bring it outside of the series. So we can write 1/9 times the sum from k equals 3 to infinity of 2 cubed is 8. So now we can write that as 8 to the k, right there, minus 1 over 9 to the k. Okay? It's a bit easier for us to look at it now. And this fraction here can be broken up further. The reason we're going to break it up further is because, according to the first convergence theorem, if the sum of a sub k and the sum of b sub k both converge, then the sum of a sub k plus b sub k also converges. So it'll be easier for us to rewrite it as 1/9 times the sum from k equals 3 to infinity of 8 to the k over 9 to the k minus the sum of k equals 3 to infinity of 1 over 9 to the k. And you have to make sure that that 1/9 is multiplied by this whole thing, so we're going to put it in parentheses. Now, according to the properties of exponents again, if this 8 to the k is raised to that k power and 9 to the k is raised to that k power, you can rewrite this further like so. Sum of k equals 3 to infinity of 8 over 9 to the k minus sum from k equals 3 to infinity of 1 over 9 to the k. And here we assume that 1 to the k will always be equal to 1 because 1 to anything is always equal to 1. So we are able to rewrite it that way. Alright, now, since we have pulled this 1/9 out here, according to our second theorem of convergence, if a sub k converges, then a constant, c times the sum of a sub k, also converges for any c, which is the set of all real numbers. So here, we pulled this constant out here, and it's not going to make any difference to whether this converges or not, according to that second theorem. And according to that first theorem, we can evaluate these two separately. So let's first look here if this part converges. So, firstly, this looks a lot like the geometric series. The geometric series, we learned, the sum from k equals 0 to infinity of r to the k, here r is 8/9, converges when the absolute value of r is less than 1. But we have a little problem. K here is equal to 3 and k here is equal to 0. Well, that can be solved by our third convergence theorem. If sum from k equals j to infinity of a sub k converges, then so does sum from k equals 0 to infinity of a sub k, because you're just taking off a finite number of terms here. So we can say that if this converges according to the geometric series test, then this too will converge, because it's the same thing as the geometric series, but subtracting those first three terms, k equals 0, k equals 1, and k equals 2. So here, we just have to check according to this, and the absolute value of r is 8/9 here, and since 8/9 is less than 1, this part converges. Great. Now we can do the same thing here for this part, applying the same logic. Here, the absolute value of r, here it was 8/9. And here the absolute value of r is 1/9. Since 1/9 is less than 1, according to the geometric series test, this part converges too. Now, once we have combined all of our theorems, this series that looked very complicated can be broken down, and you can see that since this part converges, since this part converges, and since this is a constant, the whole thing converges. And back here, you've got that this is a convergent series by the basic convergence theorems that we discussed and the geometric series comparison test.